If you guys cannot see the screen, please try to leave the session and join again. Probably it should be fixed. We'll be starting as soon as the recording is set up. All right, I'll just leave and join back just in case. Hello guys, sorry for the inconvenience. I'll be sharing my screen again, just a sec. Okay, I hope it's visible now. Guys, yes, it worked. Perfect, perfect, thank you. All right, let's start with the IGCSE physics speedrun. Hoping that you guys can hear me as well. My setup is having quite a lot of issues today. Anyways, first up, let's go over the physical quantities and units. So here are the ones listed in the syllabus. So we have length, area, volume, width, mass. These are the fundamental quantities, and all of these are derived from these individual quantities, excluding charge and current. Okay, so if you guys want, you can take a screenshot of this. This will be really handy, and you can also create formulas and find out missing variables using the units and quantities given. and this helps a lot in ADP. Okay, let's move on. We're starting today with motion. So here are the key quantities of motion. We have time and mass, and we have distance, which is the change in position. We also have speed, which is the change in distance over time, or if you want to get more specific, it's the change in displacement over time. So displacement is a vector quantity, meaning it has direction as well as magnitude. Velocity is the velocity is the change in displacement over time, and acceleration is the change in velocity over time. Force is mass times acceleration, which is also your push and pull, but it defines what mass you're moving and by how much velocity you're making a change. That is the force. And weight is the gravitational force that acts on any object, which is mass times gravitational acceleration, which is a constant for every object which has gravity. Right. Next up, whoops, I don't know what's happening. Okay, the next key quantities are momentum, which is mass times velocity. So if you have a heavy object that is moving, for example, a truck on a road, that has momentum. Impulse is the change in momentum. No, I'm sorry, wait. Okay, impulse is force times time, and it is also the change in momentum. It is also mass times change in velocity. So for example, if you have a truck and the engine speeds it up by a certain amount, so that change in velocity times the mass is the impulse that your motor has performed. The moment, which by the way you should not confuse with momentum in any case, is the force times perpendicular distance, or it is the turning effect performed by any force, right? So for example, if you have a wrench and it can be called a wrench or a spanner, by the way. So if you're having a wrench and you're using it to rotate a nut, you have a perpendicular distance, which is the distance from the nut to your hand, and you have the force, which is your hand pushing on the wrench. That defines the moment. Yes, I will be sending the presentation soon. Right. So the density is the mass divided by the volume, and volume, by the way, is distance cubed. So this can be length, width, and height. Their product is called volume. The density is how heavy something is per unit of volume. So for example, the density of water, if I remember correctly, is 1,000 kilograms per meter cubed, which means that for every cubic meter of water, there will be 1,000 grams of mass present. Pressure is force upon area. So for example, if you are pushing on a door, so you have your pressure, which is your force that you're applying with your hand versus the area of your hand. So for example, if you push a door using, for example, a needle, and you apply the same pressure, it would break right through the door, the wooden door, because the pressure here is really high, because the force is same, but the area on which the pressure acts is lower. So yes, that's the example. The change in pressure is calculated using this formula. So you have the density of the fluid. For example, if you have pressure on water, so if you have a ball that's underwater, you can use the density of the water and the gravitational constant, which for Earth is 9.8 meters per second square, and you can use the change in depth. So for example, if a 1 kg ball is 1 meter underwater versus if it is 2 meters underwater, the change in pressure can be calculated using this formula. I hope my stream is okay. Yes. Okay. Another value that you have to remember is the acceleration of free fall, which is also called the Earth's gravitational acceleration, which has these two units, meters per second square or newtons per kg. For Earth, this value is 9.8 meters per second square, but for the moon, it is 1.6 meters per second square, and you have to remember this. Right. Next, you have to know these graphs. So the ones on the upper side are the displacement versus time graphs. So if there's a constant velocity, you can see the graph goes above in a straight line. And velocity here is the gradient of this displacement time graph, because velocity equals displacement upon time. So when the velocity is constant, the gradient of this graph is also constant. if you're accelerating, so we know that acceleration is the change in velocity over time. The graph will curve upward like this because the gradient of the graph has to be increasing because velocity here is increasing. And it is the opposite with deceleration, which means the gradient of the graph goes down. We also have the velocity time graphs, which are at the bottom. So this one is constant velocity, and this one is acceleration. So we can just see the velocity goes up. And okay, this graph is wrong. Please, yeah, please ignore this one. This graph should be the downfall. Okay. Displacement, yes, someone in chat says, if you're correct, displacement is almost the same as distance, just with direction. That is correct. Yes, displacement is pretty similar to distance, but you're also taking in context the direction. So for example, if you go 1 meter ahead and come 1 meter back, the distance you covered is 2 meters, but the displacement, because it includes direction, knows the fact that you've gone forward and back, and the final velocity is 0. Do you need to remember the gravity on the moon? It should be given to you in most questions, but if it isn't, it is advisable that you remember it. For reference, the value is 1.6 meters per second. It should probably be given in most questions. Right. Here are some other key definitions. So moment, as we discussed before, it is the turning effect of a force about a pivot. And here's the formula. The equilibrium is a state of any object where the resultant force and the resultant moment about the object are 0. So that's when the object is moving with a constant velocity and a constant rotational velocity, but its velocity isn't changing, and its turning velocity is also not changing. That's when the object is equilibrium. And it is also said that at the equilibrium, the net force and the net moment, that is the resultant force and moment, those two values will always be 0. And you can use that to calculate missing forces, for example. The center of gravity of an object is the point where the weight of an object is considered to act. I'll be showing the presentation soon, by the way. The ones looking for screenshots, you don't have to worry. Okay, so the center of gravity, it's the center point of every object, the weighted center point. That's where in physics we would consider the gravity force to act. The conservation of momentum is another law that says the total momentum in a system with no external forces remains constant. So here we look at the term system. It means an object, a singular object, or an isolated group of objects where there is no external force or external moment or any external energy given or taken. So in that scenario, the total momentum of all the objects in that system will always be constant. Okay, moving on. So here we have the springs. So the things that you need to know when you're dealing with springs in physics is the load, which is the weight or any force that is acting on the spring. And you have to also take care of the extension, which is how much the length of the spring changes. The Hooke's law dictates that the force that you apply, or the load in this case, is directly proportional to the extension of the spring. So if a spring follows the Hooke's law, the ratio of force applied to extension should be constant. So if you look at the graph on the right side, I hope you're able to look at my highlights. You can see that the left part of the graph has a constant gradient, and this means that in this part force is directly proportional to extension, and in this part the spring follows Hooke's law. But as you see ahead on this right side part, you can see the gradient changes, which means the ratio to change in force to change in extension changes, which means that in this part the string is being deformed and it doesn't follow Hooke's law. So this point between these two regions where it is following the Hooke's law and when it's not following the Hooke's law, this position is called the limit of proportionality. It is the limit of load that you can apply to an object, in which case it keeps following Hooke's law, right? Beyond this limit, the extension increases exponentially. So you can see that the extension increases more even with less and less amounts of force. But you don't necessarily need to know this, but you do need to know this in the context of the graph, which is the gradient decreases, right? You can also see the diagram at the bottom here. So as you're increasing the amounts of load, let me just zoom it in, right? So as you increase the amounts of load, you can see that the extension increases, but proportionally only up to a point. In the fifth case, the extension is more than it should have been, which means the spring is being deformed and it doesn't follow the Hooke's law anymore. Yes, you do need to know about plastic deformation, but not by its exact name, which is plastic deformation. You just need to know that this thing happens when the Hooke's law isn't being followed anymore. Right, moving on. Let's look at energy. So here are listed the energy stores, or this is where an object or a set of objects can store the energy. And here are the methods by which energy is transferred. So kinetic energy is when an object is moving, and because it is moving, it has the energy that is momentum, right? The formula for this is half mv squared, but we'll look through all the formulas later. The gravitational potential energy is when an object is in a gravitational field, but it isn't moving down. So for example, if there's an airplane high up in the sky, it has tons of gravitational potential energy because it is far from a gravitational field, but the gravitational field does act on it. Elastic energy is, for example, what we saw in springs. So the recoil force, that is the elastic energy. It exists in objects that are stretched, compressed, or bent, which includes rubber bands, bent metals, springs, stuff like that. Magnetic energy is pretty similar to gravitational energy, except it applies in the context of magnets. So for example, if there are two magnets which attract each other, but they're not touching each other, so they're far away, they have energy because they have the potential to move towards each other, which they would do by force, which is an energy transfer. So because those magnets have the potential to move, they are considered an energy store. Electrostatic energy, whoops, I'm so sorry. Okay, electrostatic energy is the energy due to interactions of electric charge. So for example, if there's an electric field which is emitted by a charged object, and there's another object close to it that is willing to be repelled or attracted because maybe it has the same or different electric charge, those two objects have an electrostatic energy store because they have the potential to move towards or far away from each other. The same applies to chemical energy, which is the energy stored in elements, bonds, or compounds, which means if there are some chemical ingredients that have the potential to react with each other, they have energy which they might give out, for example, by using an exothermic reaction. An example of this is burning. So heating and then the electromagnetic waves or infrared heat are given out. That is the energy released by the chemical energy store most of the time. Nuclear energy is the energy stored in the nuclei of atoms. So for example, the hydrogen atoms that are inside the sun and they're reacting by nuclear fusion to release energy, they have a lot of nuclear energy in their energy stores. And the same thing applies to thermal energy, which is energy stored in warm objects. And these are the energy transfers by which all of these energy stores can be converted or transmitted from one object to another. All right, moving on. These are the equations and facts about energy that you need to know about. Kinetic energy is energy in moving objects. As I told you, the formula is half times mass times velocity squared. So for example, if there's an object moving at 1 kilogram at 10 meters per second squared of 10 meters per second velocity, the kinetic energy would be 1 times 10 squared divided by 2, which is 50 joules. Okay, someone ping me. Make results transfers to sure mark. This will be there as a results channel, which you will get to know about. Okay, gravitational potential energy is the energy in elevated objects or objects which are far from an object which has a gravitational field, but it is trying to attract that object. For example, an airplane over the earth. I told you this example already. So the formula for this is that the change of potential energy is the mass times the gravitational constant times the change in height. So for example, if an airplane changes its height by 100 meters, and if it has a weight of 10,000 kilograms, a mass of 10,000 kilograms, you would calculate it like this. So if you have 10,000 times the change in height, which is 100, and times the gravitational constant, which is 9.8, you could see that the change in gravitational potential, what on earth is happening? The change in gravitational potential energy is 9.8 million joules for that airplane. The work done is the change in energy or the transfer in energy, which is done by these methods that we already discussed: forces, current, heating, sound, all of that stuff. Forgive me. Right. Efficiency is the ratio of useful work done to the energy consumed. So for example, if you have a burning reaction, okay, how do you rearrange it? We won't be going through the rearrangement of these equations because that's part of mathematics. Anyways, the efficiency, forgive me, it is the useful energy output upon total energy input. So for example, if a motor uses 100 joules of energy, but it only changes the kinetic energy by 80 joules, the efficiency in this case would be 80% or 0.8. The power done is the change in work, or which is the work done per unit time. Yes. Okay, moving on. Energy sources, which we already discussed, but we need to go through these in detail because they are part of questions a lot of the times. So in chemical energy, we have fossil fuels or biofuels, both of which, no, fossil fuels are extracted from the Earth's crust, but biofuels are created using fermentation and decomposition. These two can be burned to generate internal or thermal energy, which is heat, which can be converted to another energy type, for example, electricity that we use. Water can also be used as an energy source. So this includes harvesting energy from tides and using hydroelectric dams, which means the water would fill up and then you have a dam which has a turbine which would rotate as water passes through it, generating energy through a method that we will discuss later. We also have geothermal energy, which is the heat within the earth that is extracted. We also have nuclear energy, which is nuclear fission that we're already doing. The sun does perform nuclear fusion to release the energy in form of heat and light that we experience today, which comes under solar energy. Okay, so this is one really important fact that is mentioned in tons of questions, which is except for geothermal, nuclear, and tidal energy sources, the rest of all these sources are initially or ultimately taken from energy from the sun. So for example, if we look at biofuels, biofuels come from plants that have gone through death, but those plants used photosynthesis, that is harvesting energy from sunlight, to create their food or their chemical compositions that we burn for chemical energy. We can see that the sun is the source of energy in this case. Right, moving on. Pressure. It is the force per unit area, as we discussed. So for example, if there is a cube that's lying under the water exerts a pressure on that cube to push it down or up. It is distributed evenly across rounded or spherical structures, more than it is on sharper edges. So for example, if you try to hold an egg and squeeze it by all directions, you'll notice that it doesn't crack. But if you pierce it from only one direction by, for example, banging a knife on it, it will break easily. So so you can see that pressure is distributed across the egg's surface area much more evenly. Okay, so pressure under a fluid increases as depth increases. As you get deeper, the pressure on you increases. I know that swimmers have experienced this because diving takes a lot of resilience, because there's a lot of pressure from the water above you that's acting on you. The formula to calculate this change in pressure is density times gravitational acceleration times the change in height. Okay, wait, pressure is inversely proportional to yes, it is inversely proportional. So there's this experiment that has gone famous throughout the times. So if you're trying to squeeze an egg, you'll notice that it's really hard to break it because the pressure that is put on it is much lesser, because the area that is the area of the force that you're putting, that's higher because you're trying to squeeze it from all directions. Pressure, by the way, is in 2 dimensions. As I showed you in the initial slide, the unit of pressure is let me just show you again. If we look at pressure, let me just find it. Yes, it is in pascals or newtons per meter squared, which means it is inversely proportional in squared to the depth. Okay, so this was the formula. Okay, let's move on to the next section, which is matter. So there are 3 states of matter in our syllabus. There are also more that aren't in our syllabus, but these are the ones that we have to know about. In solids, the particles of the object are really closely packed and they vibrate about a fixed position. This vibration increases with increasing temperature up to a point where these particles feel the will to freely move, and that's when they convert to liquids, where the particles are less close. They do vibrate, but they also move freely due to the increased temperature. This movement speed does increase as the temperature increases further, up to the point where the state of matter is gas, where the particles are really far apart and they move freely with a high velocity and bounce off each other, and they also bounce off from the containers which hold the gas, which is also your pressure. This movement speed increases with increasing temperature. So you'll notice that, for example, if you have a gas cylinder and you heat it, the pressure acting on that cylinder will increase. Okay, so this is the one thing that we have to know about, which determines the states of matter and the movement of particles. It is called the kinetic model of particles. Yes. In this, we have to know all of these facts, which are that all matter consists of simple particles which are constantly in motion or vibration. The arrangement or spacing between these particles determines the state of matter. So you can see in these diagrams, as the space between these particles increases, the state of matter goes from being a solid to being a liquid to being a gas. Yes. This temperature is proportional to particle motion and to the distance between these particles. This movement is least, and this kinetic energy within the particles is also least when the temperature reaches absolute zero. And you have to remember this value of temperature, which is minus 273.15 degrees Celsius or 0 Kelvin. At this point, the particles have the least kinetic energy or velocity. The pressure in gases is caused by particle collisions with surfaces, as we discussed. So for example, in this cube, when these particles collide with the edges of the cube, this edge of the cube will experience force or pressure. A Brownian motion is a proof of this random movement of particles. So you can see right here, as the particles move and collide with this big particle, this particle also moves because it experiences a change in momentum due to the collision. This movement can be seen by microscopes and is referred to as Brownian motion. There's this equation that you have to know for gases. If the amount of gas or the mass of gas in a container is the same, pressure is inversely proportional to volume. So if you compress it, for example, the pressure that this gas exerts is much more. So for example, if you have a syringe and you cover the other end of it with your thumb and you squeeze the gas inside it by pressing on the syringe, you'll notice that you find it harder and harder to squeeze the gas as you squeeze it further, which is the increase in pressure by that gas. Okay, so this is how states change So when you're heating or cooling an object, for example, when you're heating it, it undergoes melting, which is solid to liquid, or boiling, which is liquid to gas. This is where the temperature stays constant while energy is absorbed. For example, if you're boiling water in a stove, when the water reaches the temperature of 100 degrees Celsius, the particles of the water will convert to gas, but the temperature between this change of state of matter will always be 100 degrees Celsius. This also stands true for condensation, or for freezing, which is when the temperature stays constant when energy is released. So a melting ice cube will have a constant temperature of 0 degrees Celsius. So this is the difference between evaporation and boiling. In evaporation, particles on the surface of the liquid turn into gas, and it happens below the boiling point. But in boiling, particles throughout the liquid turn into gas and form bubbles, which you cannot see in evaporation, but you can in boiling. And it happens beyond the boiling point, for example, 100 degrees Celsius for water. Yes, this is the method list of thermal energy transfer. So first of all, we have conduction, which is the vibration in the lattice molecules and solids. So if you heat, for example, a metal rod from one side, the lattice of the particles in that metal will vibrate and make particles near it vibrate, therefore transferring heat. And it is also transferred by delocalized electrons in the structure of metals, which I'm sure you guys know about chemistry. Right, let's go further. We have waves, which is next on our list. Okay, wait, I got pinged. Doesn't boiling happen with specific temperature, and evaporation would be varied? Yes, evaporation happens on most temperatures which are below the boiling point, but boiling happens on only one specific temperature, that is the boiling point, for example 100 degrees Celsius for water. Yes, moving on. Whoops. Right, so these are waves. So a wave is a process of energy transfer through oscillations, which is when energy is transferred but matter doesn't move, or it doesn't have to have a resultant change in displacement to transfer that energy. So each wave has all of these factors, which is, for example, the amplitude, which is the distance between an extreme point on a wave and its equilibrium. So for example, on this transverse wave, the amplitude would be from this stop point to the equilibrium or center of the wave. So this is your amplitude. A crest is a point on the wave with the highest amplitude. So this, and trough is the one with the lowest amplitude. Which is, for example, this. The wavelength is the distance between successive crests, or the distance which comprises of one crest and one trough. So in this case, the transverse wave has like a wavelength of 2. So this is a wavelength of 1. So for example, this would be the wavelength of this wave. So you can see there are 2 waves right here. The frequency is the rate of vibrations in a wave per second. So for example, this point, So for example, this point on a spring, how frequently it goes up and down and back up again, that is your frequency, and it's measured in hertz. The wave speed is the product of your wavelength and your frequency, and the formula is this, V equals F lambda, where F is frequency and lambda is the symbol for wavelengths. Moving on, these are the specific actions that waves can undergo. So this is reflection, where an incident ray hits a mirror and reflects again, and the angle of incidence, the angle at which the wave approaches the mirror, is equal to the angle of reflection, which is the angle by which it leaves the mirror. These angles are calculated with respect to the normal, which is perpendicular to the surface of the plane mirror. You can see the formula, which is just I equals R, the angle of incidence equals the angle of reflection. In refraction, we have to use this formula, which is N equals sine I upon sine R. N here is the refractive index, or the ratio of the speed of the wave between these two mediums. So in the diagram, you can see that here the angle of incidence is greater than the angle of refraction. So you could put these two values of I and R and get N, and you can also use that to get sin I and sin R. You can shift these variables to find any single variable. So for example, if you want the angle of refraction, this would be R equals sine inverse of sine I upon N, which you can get by just shifting these variables. The critical angle is the angle at which total internal reflection occurs, beyond which total internal reflection occurs. So for example, if the angle is 43 degrees, if you increase the angle more than that, the wave will just refract, no, it will just reflect off of the denser medium, yeah, which would be similar to your reflection, but it actually happens due to the refractive index. The diffraction is also a phenomenon that happens with waves, which is it spreads out as it passes through a gap, and it happens most when the width of that gap is equal to the wavelengths, which is when the diffraction happens at the most angle. So there are no formulae for this. There's nothing you have to know most except for this fact, but this is what happens when you have diffraction. Yes. Okay, next up we have lenses, which occur in two types, which are converging or convex lenses, or diverging and concave lenses. Converging lenses bring all the light from one source to focus. So for example, you have these two parallel rays of light approaching this lens, but because this lens is a converging lens, these two rays of light will move towards each other and intersect at this special point, which is called the focal length. So you can refer to this image, which you can always find by using this command. I'll just type it in the chat. Yes, here's the image if the bot works. Yes. Anyways, the diverging lens does not have a focal length, but it causes the rays to spread out or diverge. Yes, and it corrects short-sightedness. So if you have spectacles and if you're short-sighted, meaning you cannot see stuff at a distance really well, it is the diverging lens that fixes this issue, that corrects your internal eye lens. Similarly, long-sightedness is mitigated by using a converging lens in your glasses. Okay, so when you're drawing ray diagrams like this, there are two types of images that you might see. So these are real images and these are virtual images. So if you can see the top 4 rows of this, you can see that the images formed are actually formed by using real rays of light. But the virtual images are rays of light which are traced back from the rays of light that are actually given out by the lens. So the 5th and 6th row have virtual images which are formed beyond the lens. Yes. Moving on, just a second. We have the electromagnetic spectrum. So we have these 4 types. No, these 7 types, in fact. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So as you go down this table, the frequency of these waves will increase, but the wavelength of these waves will decrease. But the wave speed stays the same because you're looking at the speed of light. These are the variants of light, including the visible light that we can see. This falls under the electromagnetic spectrum, the part of it that our eyes can take. So radio waves are used in radio, television, astronomy, and RFID tags, which are used for identification, for example, in your hotel keycards. Microwaves are used in satellites, they're used in Bluetooth, they're used in ovens to heat stuff up. You can see these uses for the rest of the waves. I'll just give you guys a moment here to read through. Thank you in chat for this mnemonic. Raging Martians invaded Venus using X-ray guns. R standing for radio, M standing for micro, and so on. Thank you for whoever said that in the chat. You do have to memorize all of these parts of the spectrum along with their uses because they're frequently asked in your exams. Yes, you have to memorize all of this information. You do not need to know the specific wavelengths and frequencies of each of these ranges of the spectrum. This is part of your A-level syllabus. Okay, let's move on. Next up on our list is sound. So sound is the longitudinal waves which happen through matter or through air, solid, liquid, gases, all of that stuff. So frequency would relate to your pitch of the sound, while the amplitude of the wave would relate to the loudness. The speed of sound is 330 to 350 meters per second in air, but it increases as you transmit sounds in liquids and even more in solids. The frequency range for which humans can perceive sound is 20 hertz to 20,000 hertz, and you have to memorize this fact. Echoes are reflections of sound waves that might happen. For example, when sound passes through gas, but it meets a solid, so it reflects off there, and you can hear the sound multiple times. That's an echo. Ultrasound is one of the uses of sound that we have in industry. It is used for non-destructive testing and verification of materials such as metals, and it's also used for medical scanning, your ultrasound scans. Sonar probes are also used to calculate depth or distance or to identify objects. These use echoes or reflection of sound. So for example, if you transmit sound at your position and you hear an echo after a certain period of time, you can use that period of time, that value in seconds, and use the speed of sound divided by the speed of sound, and you could get your distance by which you can detect. Okay, next up we have magnetism. So these are magnetic forces which occur due to interactions between magnetic fields produced by magnets. So you can see the image of bar magnets right here. We can trace these magnetic fields by using a compass, by placing it at one of the poles, and the way at which the arrow points, just plot a point there, place the compass beyond that point, and so on. You can trace the whole electric field line magnetic field line using the compass. These magnetic metals can be magnetized under these magnetic fields, leading to attraction. So for example, if you've seen a chain of nails which is hanging off of a bar magnet, that happens because those chains, nails are magnetized by the magnetic field of that bar magnet. So they extend the magnetic field to more nails. So there are two types of magnetic materials, which are soft and hard. So soft is, for example, iron, which are really easy to magnetize, but they lose their magnetism really quickly. These are used in electromagnets and transformers and that stuff. Hard materials are much more difficult to magnetize, but they lose their magnetism much more slowly. So examples for these are hard steel and neodymium, which is one of the most efficient forms of magnetic metal. Yes. Electromagnets, as I referred to, they consist of a coil wrapped around these soft metals. They turn on and produce a magnetic field when current passes through that wire. These factors which affect the strength of this magnetic field and the distance at which it can appear, they are the current and the number of turns. Moving on, we have electricity. So these are the units of electricity that you have to know about. EMF and potential difference. EMF, by the way, stands for electromotive force. These are variants of voltage which pass through either of the power source or through a circuit component. So you could measure, for example, the PD across a light bulb using a voltmeter. Forgive me. Um, Resistance is the ratio between the voltage and the current, which is the rate of charge passing through a wire or through metal. It is equal to inverse of the gradient of the voltage and current graph. So you can see the graph right here. We can plot the voltage that passes through any component of a circuit versus its current, like so. The gradient of this, if you divide it by 1 like so, you can find the resistance of that circuit component. The power which a battery can induce or a component can use has these three formulas, which is the voltage that passes through it versus the current that passes through it, multiplied. It is also calculatable using I square R or V square upon R. The energy that can be taken up by any, for example, light bulb, is calculated by using power into time, or IVT, or even I square into R into T, or V square upon R times time. As you wish. The unit for this is kilowatt hour, but you could also use watt hour, which is not usually recommended. So 1 kilowatt hour is equal to 3.6 megajoules, or 3600 kilojoules. So you can see these graphs of current and voltage right here. So the first one occurs with normal metallic conductors. So for example, your wires, coils, resistors. That's when you see a straight line passing through a graph like that. A diode lets current pass through only one direction as good as it can. So the graph looks like this. It is biased based on which direction the current goes through, or the voltage is applied to. Whoops, I'm so sorry. A filament lamp has voltage increasing with proportion to current, because as you apply a greater voltage to a filament lamp, its resistance would increase because it heats up. So you can see that this gradient decreases, which means the resistance increases as voltage or current increase. Okay, next up we have our circuit symbols, which you certainly have to know for your IGCSE physics examination. Have a good look. We have ammeters and voltmeters, which are probes. We have all of these components, lamps, LEDs, resistors, that we're going to be using in our circuit diagrams. Right, moving on. So these are the things that you need to know about electric circuits. So the current stays the same at every point in a series circuit. So if all of your components, for example, if you have multiple resistors, multiple light bulbs, if you put them next to one another in a circuit without any branching, it results in a situation where the current at any point in the circuit is exactly the same. Voltage, on the other hand, stays the same in branches of parallel circuits. So which means if you have like 3 branches extruding from one battery, the voltage in the total voltage of each of those 3 branches would be exactly the same. But voltage distributes in the ratio of resistance in each component of a series circuit. So for example, if you have 2 bulbs in a series circuit and they have exactly the same resistance, both of those bulbs would achieve exactly half the voltage of the battery or the power source. But current distributes as it passes into branches of a parallel circuit. So all of those branches would not have the current equal to the main current that is being given out by the power source or battery, but rather it is distributed into those multiple branches. Resistance changes in a very special way as you go from series circuit to parallel circuits. In the series circuit, the total resistance is just the sum of the resistances of each of the components in that series. But in a parallel circuit or across multiple branches, the combined resistance of all of those branches can be calculated using this formula. Okay, we'll be moving on. Potential dividers are a special kind of circuit which are used to divide the voltage or distribute it across multiple areas. So for example, if you have one resistor here, and this, by the way, is your variable resistor that you can regulate, and this is a normal fixed resistor, the voltage passing through this voltmeter right here would be the source voltage multiplied by the resistance of this versus upon the resistance of the all of the components in this series. So here's the formula. So V1, the voltage of this, is equal to Vs times R1 upon all of the other resistances and also R1. In this circuit, V1 increases as the source voltage increases, but it decreases it also increases when this resistance increases, because as you know, the formula V equals I times R. This resistance increasing would increase the voltage across it. But if the resistance of this resistor increases, the voltage of this voltmeter would decrease, because the ratio of voltage spread across all of these results in a situation where this voltmeter has a lower voltage, right? This is a circuit used very frequently in, for example, regulators, which are used for light dimming, fan speed control, stuff like that. These are the other circuits that you'll encounter in your IGCSE syllabus. So a relay is a circuit which controls whether current passes through one part of a different circuit. So you can see this relay part right here. This would be your electromagnet, which pulls this switch onto itself, closing the other circuit that lies over here. These are used in car engines, factories, alarms. These are used in scenarios where you need to have multiple isolated circuits, but one circuit controls another. Transformers are also a type of component. They're used to convert the voltage of one source of current into a different voltage. So you can change the voltage of any AC electricity using a transformer. And this is the equation you have to know. Vp upon Vs equals Np upon Ns. Here, V stands for the voltage and N stands for the number of turns across a coil. There are two types of transformers, step up and step down. So a step up transformer increases the voltage from the primary coil to the secondary one, but the step down one decreases it. This diagram of a transformer, this is a step down transformer, because you can see the number of turns in the secondary coil is much lower. Okay, we'll be moving on in 1 minute. Will a transformer not work for DC current? No, it will not. You need to have a changing current source, which is your AC alternating current. That's when a transformer actually works. Okay, let's move on. So these are the points of safety that you have to know when you're designing or working your way through a circuit. So main circuits usually contain a live wire, neutral wire, and an earth wire, which is used on your insulation to make sure that no current gives a shock or electrocutes the user of a circuit, which could be a really dangerous phenomenon or event. Yes. Switches and fuses must be attached to the live wire, because that's where you regulate whether current makes its way into your circuit. These scenarios could be extremely dangerous when you're working with circuits. So for example, damaged insulation would mean that your circuit is exposed, and if a user touches the circuit, they could get an electric shock, and they could fall into a coma, they could experience death. That kind of dangerous stuff happens. If you have overheated cables, that really That's really dangerous because a user touching one of those parts of a circuit which is overheated could seriously burn them. It also wastes a lot of energy and it might set your place on fire. Damp conditions are one extremely dangerous and extremely underrated source of damage. This is because water in the atmosphere is a really good conductor and it would let current across a lot of the components, maybe even cause a short circuit. Right. Excess current passing through any component or any switch or any extension could lead to overheating, insulation damage, all of that stuff. This is one thing that you must prevent when designing your circuit. The precautions that you can take versus these dangerous scenarios, they are fuses, which would turn off the circuit, which would burn up and turn off the circuit in case excess current passes through, or for example, if there's a short circuit. Trip switches do the same thing, but they can be turned back on. The rating of the fuse or trip switch that you use should always be greater than the ideal amount of current passing through your live wire. Another precaution that you could use is double insulating your electrical circuit and earthing the outside part of the circuit which a user is likely to touch. Moving on. Electromagnetic forces are generated when a current flows across a wire, but there's also magnetic field formed. Yes. So you can see we can use this rule, which is your Fleming's left-hand rule, to find the direction of force from your current and magnetic field. So when current flows through a coil, these are the poles that are formed. So if the current is going clockwise on one end of the coil, that's where the south pole is formed, but when it's going anti-clockwise through the other end, that's when the north pole forms. This is one thing that could really help. Yes. The factors affecting the strength of this force that is created is the number of turns of the coil that you're using, the strength of the current, and the strength of the magnetic field. Electromagnetic induction is the very opposite of creating a force using an electromagnet. This is done when a wire moves perpendicular to magnetic field. Basically, it cuts through magnetic field lines. That is when electrical current is induced into the wire. This concept is used in generators, which perform generation of electricity from maybe mechanical or thermal energy. They're also used in sensors to detect movement and stuff. They're also found using a similar circuit to those in electric motors. To create a generator, you need a pair of magnets, as in this diagram, a brushed wire that would touch this split ring commutator. And you can attach your components to these ends of the split ring. In this case, we use the Fleming's right-hand rule. And guys, do make sure to not be confused between left-hand and right-hand rules. Right-hand rule is the one that you use when you're inducing current and when you're applying force. But the left-hand rule is used when you're creating a force from electricity. So motors use the left-hand rule, but generators use the right-hand rule. Okay, moving on. Let's go to nuclear physics. And for this, special thanks to Milk for helping out in creating the presentation. So here's the basic structure of an atom that you have to know, even in physics, apart from chemistry. You have protons and neutrons in your nucleus, and you have electrons orbiting this nucleus. The proton number is at the bottom left of the element symbol. That tells you like how many protons and electrons a neutral atom has. The nucleon number is the one that you find on top of any element at the periodic table. It tells you how many neutrons and protons combined there are in the atom. To find the number of neutrons, you have to subtract the nucleon number from the proton number. That gives you the number of neutrons. And this differs across each isotope. which is, and by the way, an isotope is a variant of an element with a different neutron number. So for example, chlorine 35 has 35 nucleons, but chlorine 37 has 37 nucleons, and it has 2 more neutrons. Yes. So some of these isotopes get too unstable because they have too many neutrons and they're radioactive, meaning that they can decay. And yes, this is okay. So when an atom goes through decay, a neutron, so I'll tell you about this later, but it releases either an alpha particle, a beta particle, or a gamma ray. And this is what you would normally call radiation. So this atom structure was proven by the famous Rutherford's experiment, and you absolutely have to know this. So this is an experiment where the great scientist Rutherford emitted a lot of alpha particles, which are basically nuclei of a helium atom. So Rutherford beamed these alpha particles at atoms of gold. So there was a gold foil through which these alpha particles were passed through, and a lot of the alpha particles passed right through the atom, but some of them got deflected like so, and some of them got slightly deflected like this. So this tells you that an atom consists of mainly empty space, because alpha particles are positively charged, and if they're passing right through most of the regions, this tells you that most of the regions don't have any charge on them, or basically they're empty. When alpha particles are deflected slightly, or sometimes they just turn right back, that happens because there is an accumulation of concentrated positive charge in the center of every atom that repels these alpha particles back towards their source. Yes. Okay, we'll be moving on. So these are processes that you can apply to any atom or nucleus. They're called nuclear fusion and nuclear fission. So nuclear fission is when an atom is split apart. It involves a heavy element being split by a neutron into a smaller nuclei. So for example, if you have uranium and you throw a beam of neutrons on it, it would split it apart into multiple different types, multiple different smaller elements, atoms. Nuclear fusion, on the hand, is what you see happening inside the sun. It is the combining of two atoms, two lighter atoms, which are forced under really high pressure and under really hot conditions to form a bigger nucleus. So the sun consists of a fuel of mostly hydrogen, which combines together to form bigger atoms, for example, helium, lithium, and so on. In both reactions, you would see the total mass of the atoms in the product is less than the combined mass of the reactants. So, for example, the helium formed would have a really slight decrease in mass compared to the two individual hydrogen atoms from which they were formed. This decrease in mass explains the release of energy given out by this nuclear fusion. So the famous formula E equals mc squared tells you that matter is just energy compressed into a smaller form, and energy is given out when matter, the amount of matter or the mass decreases. Right, moving on. This is the process that I told you about, radioactive decay, and this makes a major part of nuclear physics that you have to know. This is when a lot of unstable isotopes of a lot of heavy atoms have too many neutrons, and they can't stay in that stable state for really long. So they decay, or they lose part of their atom into three possibilities. So we have alpha decay, which is a helium nucleus being released from an atom. So because a helium nucleus consists of 2 protons and 2 neutrons, that is the part of this atom that the larger atom gets rid of to achieve stability. And this alpha particle is radioactive and it is ionizing. Means it has the ability or the potential to rip electrons off of other atoms that it collides with. And these are the exact alpha particles that were used in this Rutherford's experiment. Another type is gamma decay, which is an atom just releasing energy in form of a gamma ray into the surroundings. They are usually the least ionizing, but they are really highly penetrating compared to alpha particles, which are very highly ionizing, means because they're helium nuclei, they have a lack of electrons. They have the ability to rip apart of these electrons very strongly, but they are very weakly penetrating. I'm talking about alpha particles because helium nuclei, they are much larger than photons of gamma rays or beta particles, which are mainly electrons. So beta decay happens when a neutron inside an atom converts itself into a proton and a beta particle, which is an electron, and it's thrown off at a really high speed. So these are between alpha and gamma when we're considering penetration and ionizing strengths, meaning they're more penetrating and more ionizing compared to okay, they're more penetrating compared to alpha, but they're more ionizing compared to gamma, right? These types of decay are both random and spontaneous, meaning that it is impossible to predict when an atom would decay into smaller atoms, and it is also not influenced by any outside factors, for example, temperature or amount of energy thrown at it, whatever. Nothing really predicts this decay rate or influences this decay rate, but there is a pattern using which you can tell the amount of decays that would happen at any second. So there is this concept called a half-life, which is the amount of time it would take for half of the atoms and any mass to decay. So you could have a half-life for, of example, a few years, and it would take all those few years for half of the atoms to decay and release one of alpha, gamma, or beta. So a graph of the decay rate versus time goes down logarithmically. So that means it goes down really fast at the start because the decay rate is really high. But as atoms decay, the half-life and because the decay rate depends on the number of atoms that exist, so this downfall in the graph decreases, right? There's also this concept of called the count rates. That is the unit used to measure radioactivity or decay rate. It is the amount of times an ionizing particle or ray is picked up from a Geiger counter, which is a sensor of radioactivity. So distance from the source and direction of counter does affect the count rate, but it does not affect the half-life of a source. So half-life of any radioactive isotope is predefined and it is constant. You could search up the half-life of any radioactive atom, for example, uranium. So if I do a quick search right here, let's say uranium half-life, let's see what Google has for us. Okay, standard, I search, okay, it doesn't let me. But the point is, all of these isotopes have a predefined half-life, but the count rate depends on the mass and the distance from this mass of radioactive atoms. Okay, that is all that we're going to be covering today, except for the last thing that we have, space physics. And these are, by the way, the notes of Notion that I had released publicly. I'll just do it once again for all of you. One sec. Yes, there you go. These are the notes that I made for space physics. So let's just skim through the facts. The Earth rotates around its axis tilted by 23.5 degrees Celsius, and it revolves around the Sun one revolution happens in 1 year, and the seasons alternate due to this revolution. You can see the table of seasons based on the months of the year that's currently ongoing. The moon's position relative to the earth causes the moon phases, and these phases are determined by these terms: gibbous, meaning most of the moon is illuminated; crescent, meaning a very less part of the moon is illuminated; waxing means like across time the moon will brighten up, and waning means that it will darken down. So for example, waxing gibbous, waning crescent, these are the moon phases that you could generate. Sorry. One revolution of the moon happens every 27.5 days, or approximately every month. This document, I've shared it. One sec, I'll just share it again for you. Yes. So moving on, the solar system. It consists of planets, all of these, and then you have your asteroid belt, and then you have your outer gas giants. So Mercury, Venus, Earth, Mars. Then you have the asteroid belt. Then you have Jupiter, Saturn, Uranus, and Neptune. Dwarf planets are usually located beyond Neptune. So examples are Pluto, Eris, etc. You don't need to remember the name of Eris, but you need to know about Pluto. Moons are satellites that orbit planets and dwarf planets which are naturally occurring. So for example, if we let out a satellite from a rocket ship that isn't a moon, it has to be naturally occurring. Waxing is getting brighter and waning is getting darker. Yes. Then you have your asteroids and meteoroids and comets. Comets are basically frozen balls of gas, rock, and dust. They heat up as they approach the sun, and they let out traces of dust, which are actually visible a lot of times. They point away from the sun. Yes, thank you. Yes. Okay. Gravity of stars holds planets in elliptical orbits. So you can see this diagram of orbits. These are ellipses, which are not perfect circles, but you could think of them as stretched circles. These are what ellipses are. Yes. Okay, so let's talk about orbits. There's this factor, gravitational field strength, which is newtons per kg, and for Earth, as I talked about, it's 9.8. This depends on the mass of the planet and moon, and it decreases as you get further. There's actually an equation for the gravitational field strength. So it is g, gravitational constant, times the mass of the two objects. Okay, let me just not get into that. The formula is g times m1 times m2 upon distance squared, but that's not in the syllabus. Anyways, these orbits are elliptical due to the sun's gravity. So that means as an object gets closer to the sun, it accelerates, but as it gets further, it decelerates. And as I told you, elliptical is different from circular, and during acceleration, gravitational potential energy turns into kinetic energy, vice versa for deceleration. The sun is actually not the center of the orbit, it is the focus, which is the point where gravity acts and pulls all of these objects into their orbit. The orbital speed is greatest nearest to the sun. That's because acceleration has happened as you're nearing it. And comets usually follow this acceleration pattern. You can see this diagram that shows that the Earth's velocity is this way, and there's a radius which determines the gravitational field, which pulls the Earth towards the sun on its circular orbit at places like that. So the average orbital speed has this formula: 2 pi times radius of the orbit divided by its time. This is your orbital speed. I'll send this document on this community events thread real soon. Okay, The sun is a star of medium size. It consists mostly of hydrogen and helium, although there are a few of the heavier elements such as lithium and so on. It exists in the state of matter known as plasma because of the extreme temperature. It is powered by nuclear fusion, which is the conversion of hydrogen into heavier elements. This nuclear fusion releases energy in the form of electromagnetic waves, infrared, visible light, ultraviolet, and a little bit of gamma, which is actually absorbed by the plasma itself, so it doesn't really come out as much. The Earth orbits the Sun in the habitable zone, and this is where the temperature is normal in our perspective, which means it's neither too hot and it's nor too cold for life to exist. And for life, there must be liquid water. Okay, let's talk about stars now. Galaxies are clusters made of billions of stars. For example, the Milky Way, which contains the Sun and Earth and all of us on it. The diameter of a galaxy would be approximately 100 light years. It could be a lot more, a lot less, but the average diameter is this. Astronomical distances, are they're measured in light years. So this is the distance traveled by light in a vacuum in 1 year. It is equal to 9.5 times 10 to the power 15 meters. And you have to remember this calculation and this value of the light year. The life cycle of a star is as follows. So there is a nebula, which is a cloud of gas and dust, which compresses into a star. And nebula are molecular clouds. They contain hydrogen, and as they collapse and heat up to gravity, they are later called a protostar. This is stable when the inward force of gravity acting on the atoms inside of this molecular cloud equals the outward force due to high temperature and pressure, radiation pressure. So that is when the star is formed, and that is when nuclear fusion starts within the star and releases a lot of the energy. So when the star is nearing the end of its age, 100,000 light years. Yeah, you're right. I'm sorry. 100K light years. My bad. So when the star is nearing the end of its age, it runs out of hydrogen fuel. That is when most stars expand to form red giants, and red giants are formed when hydrogen runs out, and nuclear fusion becomes really, really slow. And that is when the heat is much less, which results in the star contracting, and this contraction just heats up the star much more, and that starts helium fusion, which is helium turning into beryllium and heavier elements. So you can see the diagram right here. I'll also tell you this, for more massive stars, which are like more than 8 solar masses, they turn into red supergiants, and these are much larger than red giants. This is what happens. You can see the composition of red supergiant. You can see hydrogen, and there's helium and carbon and oxygen and all of these different elements within the core of the star. So this red supergiant would undergo a supernova one day when no more fusion can happen after a lot of compression. And there are two possibilities: a black hole or a neutron star, which will be formed at the center of the supernova. Okay, so here you can see the diagram for the summary of the star's life cycle. And here are the phenomena of radiation and light that happen through the universe. Redshift is when the observed wavelength of any electromagnetic radiation changes, it increases. So this is caused by Doppler effect. You can see that this redshift can be used to calculate the Hubble constant, which I'll explain, and it supports the Big Bang theory. So this is a technique that astronomers use, which is called spectroscopy. So it is basically a map of light rays emitted or reflected by any stars, which they can use to find the composition, meaning the atoms and elements that the star consists of, right? CMBR is the radiation that we can perceive that is spread throughout the universe. You can see the details right here. The Hubble's law dictates that the speed of galaxy recession is directly proportional to the distance from Earth. And this is also dictated by the Hubble constant, which is the ratio of speed of galaxy recession versus the distance of Earth. You can see these two equations. So h0 here is the Hubble constant, v is the velocity of recession, and d is the distance from Earth. And you can just inverse this to find the inverse Hubble constant. So the current estimate for the Hubble constant that we humans have calculated is 2.2 times 10 to the minus 18. And the inverse represents the age of universe. And the current estimate is 4.5 times 10 to the 17th seconds, which is 14.5 billion years. So you have to remember these two values for examination. And because we have been able to calculate an age of the universe, it means that there was a time when the universe was formed from the Big Bang. And yeah, that is when all of the atoms inside the universe were present at a single point. Which concludes the end of space physics and the end of IGCSE physics in 1.5 hours. Thank you a lot, everyone. We'll be focusing on questions from the Discord chat now. So if you guys have any questions, feel free to post it inside chat. We have 30 more minutes for any questions. Probably we won't need all of that. Okay, you missed the whole thing. The recording will be uploaded and you'll be told about it. We'll let you know in some time. Could you explain the motor and generator stuff? Right, one sec. I hope you can still see my screen. Let me just go back to the part where motors and generators are. Yeah. So this is what a motor typically looks like from the inside. So there's a magnetic field between north pole and south pole of a motor, and when you have your current passing through this coil of wire that you have inside of this magnetic field, it rotates because of this Fleming's left-hand rule. So you can see that magnetic field and current can be used. So for example, magnetic field here would be leftward, and the current passing would be, for example, in this part, frontward. You can see that the force applied on this part of the coil would be upwards because of the Fleming's left-hand rule. To create a motor, you need this slip ring commutator and a brush of wires through which you have your current passed onto this axle and motor. So you can see because of this structure, when this motor rotates 180 degrees, the current passing through this coil will be reversed so that this motor keeps moving in its original direction. It is a similar concept that we use in electromagnetic induction or generators. That is, when you have a magnetic field and when you move this coil, this electric current is generated, which passes through this coil right into our split ring commutator, which can be connected to our components or any batteries that we have to charge. For this, we use the Fleming's right-hand rule. As you can see, you can use the right-hand rule right here. So the current would be facing, for example, in this front part of the coil, the current would be facing towards you, towards the right. You could place your middle finger that way. The field of the magnet would be from left to right. So yeah, you can use the Fleming's right-hand rule to dictate that this coil will move anti-clockwise from our perspective. Okay, I'll be sending these slides in the IG Physics channel after this session ends. The commutator, okay, so let's see this commutator. So you can see that when the coil rotates 180 degrees, what a commutator does is it reverses the direction of current passing through, so that it's always passing anti-clockwise like so, and the motor can continue to spring. So it just it just moves your current, it just reverses it halfway through. The accretion model. Sure. So when you have inside the life cycle of a star, when you have your molecular cloud which is compressing onto itself, that's called accretion, which is the accumulation of these particles into itself. So that is accretion, and an accretion disk is formed because of the rotation of all of these particles, which result in a disk being formed due to centrifugal forces. Commutator helps to reverse, yes. If it is higher than the critical angle and your light is passing through the denser medium, a total internal reflection will certainly happen. It will reflect all of it, but like mostly all of it, but that just depends on the transparency of the glass that you're using inside of your denser object. Do you need to know why the 4 planets are rocky? That's just that's just because you do have to know. Okay, we will be waiting 5 more minutes for any questions that you guys might have. If we're done. Okay. We use left hand for DC and right hand for AC. No, that is wrong. We use the Fleming's left hand rule for when we're, wait, let me show you the slide. For when we have forces generated from electricity. So that's in your motors, that's when you use the left hand rule. You're using induction, you're using the right hand rule for cases of induction where you're generating electricity from motion and a magnetic field. That's when you use the right hand rule. They have to memorize the diagram of the sun when the fusion is happening. If you're talking about this diagram, yes you do. This is the possibility of a life cycle of a star depending on the mass of the star. You have to remember all of these steps, the phases, what causes all of this. Yes you do. The difference between split ring. So the structure is mostly the same, but the difference is that your split ring commutators are used in induction circuits because they're connected in this method to your components. And the difference is this split ring commutator does rotate, but this commutator rotates to reverse the current for your motor. But this is called by manual rotation. There is no structural difference really, they do the exact same thing. Okay, so momentum is mass times velocity. So for example, if you have a truck that's moving on a road with a high speed, that has a momentum which is much higher than, for example, a car which has a lower mass or is moving with a lower speed. Yeah, that's momentum for you. It's pretty easy. Electric circuits. If you guys have any doubts relating to the concepts, you can go through the recording of this session. But I'll just show you the slides. Yeah. There you go. This is the stuff that you have to know. How current and voltage splits in series and parallel circuits, and the formulae for calculating combined resistance. For potential dividers, this is the circuit diagram that you have to use. And this is what you use to divide the voltage in the ratio of these two resistors. This is the formula. Yeah. These are the other circuits. relays are used for triggering other parts of different circuits from a totally different circuit. So for example, when you have your car and you're moving your car key, that's when a relay is used to ignite the car engine using a spark. That's where a relay is used. Yes. Can the particle that goes through radioactive decay also lose electrons, or is just protons, neutrons? Okay, so let me just explain the three types of decay real quick. Yeah, in alpha decay, the electron loses two protons and two neutrons from its nucleus. In gamma decay, it doesn't lose any mass really. In beta decay, it loses a neutron, but it gains a proton. So that's when a neutron is converted into a proton and a beta particle, which is your electron. The PV constant. So the PV constant part, let me just find it real quick. One sec. Yeah. So this dictates that the pressure in a container full of gas is inversely proportional to the volume of the gas, given that the mass is constant. So you might have heard of this equation, PV equals nRT. This is not really in the syllabus, but n here is the number of moles of gas. R and T are just other constants and variables that define the mass. The recording will be sent to you soon. You'll be informed about it in the IGCSE physics channel. Galactic redshifts. Okay. Okay, I hope you guys can hear me. Redshift is when the wavelengths of electromagnetic radiation, which is observed by you, increases because of the Doppler effect. So when you have an object that's moving away from you, emitting light, the wavelengths of light that you see will be much lower than the wavelength of light that object is actually trying to emit. This can be used to calculate the speed of the recession, and yeah, it's just simply Doppler effect. Okay, to transformers change the voltage of the current line. Yes, so let me just show you what transformers look like. So what they do is they convert a specific voltage into another specific voltage in the ratio of these turns. So the voltage across this coil doesn't really change, but it influences the voltage of the current in the secondary coil. Okay, we have 2 minutes to go. We're confused on the topic of potential dividers. Let me just show you real quick once again. Okay, so this is when you have a really high source voltage, but you need a part of that voltage across one of your other components. So you have multiple resistors set up like this, and the formula that you use is that this voltage recorded by the voltmeter will be equal to the resistance of this upon the total resistance in the main branch of the circuit. So for example, if you have a 12-volt power supply, you could use a 1 ohm resistor here and a 3 ohm resistor here to get 3 volts here. So that would be because 3 is equal to 12 into 1 upon 4. That's how you calculate it. Explain how EMF is generated. EMF, the electromotive force, it is just yeah, it is just the voltage around the battery or the power supply. It's just nothing else. I didn't get what you mean by your steps and high. Okay, so there are these two types of orbits that this person is talking about. So there is the geostationary object orbit. When a satellite orbits the Earth at a specific velocity at which it only targets one point of the Earth. That is, it moves in cohesion with the Earth's rotation. Low Earth orbits are orbits for satellites where the radius of orbit is much lower, but the orbit speed is much higher. S waves and P waves. So P waves, let me just show you. P waves are simply longitudinal waves, and S waves are your transverse waves. That's literally all there is to it. Examples of convection, yes, you do. You do have to know. Yes, we will be sending these slides. Right, seeing as there are no more questions, this would be the ideal time to finish the session. So thank you for your time, each and every one of you who attended the session, and for the ones of you who are in October, November series, all the best for your exams. I'm sure each of you will do really well. Explain the count rate half-life thing. Okay, one sec. So I'll just search up a half-life graph for you. Half-life graph to show you guys. Yes, so you can see this image right here. So after one half-life has passed, the count rate or amount of radiation decreases by 2. And after another half-life, it halves and halves and halves again. You can see the difference in graph as the half-life decreases. The graph becomes steeper and less wide. This is, by the way, the graph of count rate that I was talking about. Learned everything in this course for 2 years. Thank you very much. By the way, just as a heads up, I've covered 99.9% of the syllabus, but you always have to cover that 1% that you think that you're weak at yourself from your textbook or your notes, or ideally from the syllabus document. So I might have covered all of the concepts here, but it is equally as important, or I would say much more important, to go through the syllabus once again on your own. A good way to revise revise before the exams, I would suggest that you compile all of your sources of information, such as books and notes and everything. So you read all that and make your own notes based on all of that stuff, so that you know for certainty that you have gone through every nook and cranny of the syllabus that's out there. So I actually did this personally. So for example, you can see in chemistry, I've covered most of the topics of the syllabus in my own notes, and you can see all of these notes that I've made. You can see the notes in biology. So all of these important concepts that you have to know, you should really compile all of them in really short notes. The notes are already shared in the specific channels, but if you really want them, I'll just share the notes again. This includes most of the contents in all of the subjects that I have. Right. This is actually one of the most ideal ways of practicing and revising. But do make sure that as you're doing your past paper questions and past papers and topicals, do make sure that the questions that you do get wrong, or those that you do mess up in, do make sure to reflect on those, to introspect, make sure of the topics that you don't know, revise those topics again, so that there is no part of the syllabus left that you might have a weakness in. All right, I guess we'll be ending the session now. Thank you very much. The slides will be shared in the IGCSE Physics channel. Thank you guys. Bye-bye.